Right now, the universe is falling apart, not in some distant future, not in theory, right now. And the strangest part is, the force that is pulling it apart is the same force that no one can see, no one can touch, and no one can explain. It is called dark energy, and it makes up 68% of everything that exists. Think about that for a second. Look around you. Every star you have ever seen, every galaxy in every photograph, every planet, every moon, every grain of dust floating in space. All of that, everything you can see or detect with any instrument ever built, makes up less than 5% of the universe. About 27% is dark matter, an invisible substance that has gravity but does not glow, does not reflect light, and has never been directly touched or captured. And the remaining 68% is dark energy, the biggest ingredient in the universe, and we have almost no idea what it is. Here is what we do know. The universe is expanding, space itself is stretching, galaxies are moving away from each other, and this has been happening since the Big Bang, about 13.8 billion years ago. Now, for a long time, scientists expected this expansion to be slowing down. That makes sense, right? Gravity pulls things together. Every galaxy is pulling on every other galaxy, so the expansion should be like a ball thrown into the air. It goes up, it slows down, and eventually it either stops or comes back down. But in 1998, two teams of scientists discovered something that changed everything. The first team was called the Supernova Cosmology Project, led by Saul Perlmutter at the Lawrence Berkeley National Laboratory. They studied 42 distant supernovae. The second team was called the High Z Supernova Search Team, led by Brian Schmidt at Mount Stromlo Observatory in Australia, and Adam Rees at the time at the University of California, Berkeley. They studied 16 distant supernovae plus 34 nearby ones. Both teams used a special type of exploding star called a Type 1a supernova. These explosions happen when a dead star called a white dwarf steals too much material from a companion star and crosses a weight limit of about 1.4 times the mass of our Sun. This limit is called the Chandrasekhar limit. When the white dwarf crosses it, the star explodes, and because the explosion always starts at roughly the same mass, it always produces roughly the same brightness. That makes Type 1a supernovae like standardized light bulbs scattered across the universe. If you know how bright the bulb actually is, and you measure how dim it looks from Earth, you can calculate how far away it is. Both teams expected to find that distant supernovae were brighter than certain predictions, which would mean the universe was slowing down. Instead, they found the opposite. The supernovae were about 20 to 25% dimmer than expected. They were farther away than they should have been. The universe was not slowing down, it was speeding up. The expansion of the universe was accelerating. This was so shocking that both teams spent months checking their work, terrified they had made a mistake. Adam Rees later recalled that the result seemed too crazy to be right. Brian Schmidt said finding an accelerating universe was like throwing a ball up in the air, and instead of having it come back down, you see it fly off faster and faster into the sky. But both teams got the same answer, independently, using different supernovae, different software, and different analysis methods. The universe was accelerating. Something invisible was pushing space apart faster and faster. That something got a name: dark energy. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for this discovery. Now, the simplest explanation for dark energy is something Einstein came up with over 100 years ago. In 1917, Einstein added a number to his equations of general relativity called the cosmological constant. Written as the Greek letter lambda, he added it for a completely different reason. Back then, everyone believed the universe was static, not expanding and not contracting. But Einstein's own equations kept telling him the universe should be either growing or shrinking. So he stuck in this extra number to hold everything still, a kind of anti-gravity built into the fabric of space. Then in 1929, Edwin Hubble discovered that the universe actually was expanding. Einstein reportedly called the cosmological constant his greatest blunder, though historians like Mario Livio have since pointed out that the exact words "greatest blunder" might have been an embellishment by physicist George Gamow, who told the story decades later. But here is the twist. When dark energy was discovered in 1998, physicists realized that Einstein's cosmological constant might have been right all along, not as a way to keep the universe still, but as a real energy built into empty space itself. If you remove every particle, every photon, every speck of matter from a region of space, there is still energy there. Vacuum energy, and that vacuum energy pushes space to expand. If the cosmological constant is the correct explanation, then dark energy has a very specific property. It never changes. It has the same strength everywhere and at every moment in time. Scientists describe this with a number called W, the equation of state parameter. For a perfect cosmological constant, W equals exactly -1. And for 25 years, every measurement we made was consistent with W equals -1. Dark energy appeared to be constant, unchanging, permanent. But not everyone was comfortable with that answer, because there is a massive problem hiding behind the cosmological constant. When physicists try to calculate how much vacuum energy empty space should contain using quantum mechanics, the answer they get is roughly 10 to the power of 120 times larger than what we actually observe. That is a 1 followed by 120 zeros. It is the most wrong prediction in the history of physics. This gap is so absurd that some physicists suspected the cosmological constant could not be the whole story. Maybe dark energy was not constant at all. Maybe it was something dynamic, something that could change over time. In 1988, two physicists, Bharat Ratra and Jim Peebles at Princeton, proposed exactly that. They suggested dark energy could be a field that slowly evolves, getting weaker or stronger as the universe ages. In 1998, Robert Caldwell, Rahul Dev, and Paul Steinhardt gave this idea a name: quintessence, a fifth element after matter, radiation, dark matter, and the cosmological constant. In quintessence models, W is not locked at -1. It can be slightly higher or lower, and it can drift over time. But proving this required a new kind of measurement. You could not just look at supernovae. You needed a way to measure the expansion of the universe at many different moments in cosmic history with extreme precision and compare them. You needed a ruler, a cosmic ruler, and that ruler already existed, frozen into the structure of the universe itself. About 380,000 years after the Big Bang, the universe was a hot, dense soup of particles and light. Sound waves were rippling through this soup. Actual sound waves, pressure waves traveling at about half the speed of light. These waves pushed matter outward in expanding shells. Then the universe cooled enough for atoms to form. The soup became transparent, the sound waves froze in place, and they left a pattern, a preferred distance between clumps of matter, about 490 million light-years in today's expanded universe. This pattern is called Baryon acoustic oscillations, BAO, and it shows up everywhere. In the distribution of galaxies across the sky, galaxies are slightly more likely to be separated by this specific distance than by any other. It is like a fingerprint pressed into the entire cosmos. If you can measure this distance at different points in the history of the universe, you can track exactly how fast space was expanding at each moment. And if dark energy is changing, the ruler will show it. The distances will not match what a constant dark energy predicts. But to use this ruler, you need to map millions of galaxies, each with a precise distance measurement. You need the biggest three-dimensional map of the universe ever built. And that is exactly what a team of scientists decided to build. In the mountains of southern Arizona, at an elevation of about 2,100 meters, there is a telescope called the Mayall 4-meter telescope at Kitt Peak National Observatory. Starting in 2018, engineers installed a new instrument on top of this telescope, an instrument unlike anything that had ever existed before. It is called DESI, the Dark Energy Spectroscopic Instrument. DESI has 5,000 tiny robotic arms. Each arm holds an optical fiber thinner than a human hair. In less than 2 minutes, all 5,000 arms swivel independently to point at 5,000 different galaxies at the same time. Light from each galaxy travels down its fiber into a bank of spectrographs that split the light into a rainbow of colors. From that rainbow, scientists can measure exactly how fast each galaxy is moving away from us and how far away it is. DESI began its main survey in May 2021. Every night, it maps roughly 100,000 new galaxies. In April 2024, the team released their first major dataset. It contained 5.7 million galaxies and quasars, the biggest three-dimensional map of the universe ever made. But the map was not just big, it was strange. When the team measured baryon acoustic oscillations at different moments in cosmic history and compared them to what a constant dark energy would predict, the numbers did not match. Dark energy appeared to be stronger in the past and weaker in the present. The equation of state parameter W was not sitting at -1, it was drifting. In March 2025, DESI released their second major dataset, 3 times more data, over 14 million objects. And the signal got stronger. Different combinations of DESI data with other measurements showed evidence for changing dark energy ranging from 2.8 sigma to 4.2 sigma. In physics, 5 sigma is the gold standard. It means there is only a 1 in 1.7 million chance the result is a fluke. DESI is not there yet, but it is getting close. Michael Levi, the director of the DESI project at Berkeley Lab, said it clearly. Whatever the nature of dark energy is, it will shape the future of our universe. It is pretty remarkable that we can look up at the sky with our telescopes and try to answer one of the biggest questions that humanity has ever asked. Kamrun Vafa at Harvard told Quantum magazine that would be amazing. It would be the most important discovery since the discovery of dark energy itself. For 25 years, dark energy looked permanent, unchanging, a fixed feature of reality. Now, for the first time, we have real evidence that it might not be. The force that makes up 68% of the universe, the force that decides how the cosmos ends, appears to be getting weaker. And that raises a terrifying question. If the force that is holding the future of the universe together is fading, what exactly happens when it is gone?
So now you know what dark energy is. You know how we found it. You know how DESI built the biggest map of the universe ever made. And you know what that map is telling us. Dark energy is getting weaker. But here is the question no one wants to answer. If the force that controls the future of the universe is changing, what happens next? Scientists have come up with 5 possible endings. Let me walk you through the most important ones. The first is called the heat death. If dark energy stays constant forever, the universe keeps expanding. Galaxies drift apart, and they never come back. In about 5 billion years, our sun will run out of fuel, swell into a red giant, and die as a cold white dwarf. Around the same time, the Milky Way crashes into Andromeda. They merge into one giant galaxy. But about 100 billion years from now, every other galaxy crosses beyond what scientists call the cosmological horizon. Their light can never reach us again. A civilization born in that era would see one single galaxy surrounded by total darkness. No evidence the Big Bang ever happened. Lawrence Krauss and Robert Scherer described this in their 2007 paper. They called it the return of a static universe. Between 1 and 100 trillion years from now, the last stars die. The smallest red dwarfs finally run out. The cosmos goes completely dark. Then, if protons decay, as some theories predict, every atom slowly dissolves into radiation over timescales of 10 to the power of 40 years. After that, only black holes remain, but even black holes evaporate. Stephen Hawking showed in 1974 that black holes slowly leak energy. A stellar black hole takes about 10 to the power of 64 years to vanish. A supermassive one, about 10 to the power of 93 years. After that, nothing. A thin, cold soup of particles drifting apart forever. No structures, no energy, no way for anything interesting to ever happen again. Fred Adams and Gregory Laughlin published the most detailed timeline of this in 1997. They called the final chapter the Dark Era, the era that never ends. The second ending is the Big Crunch. If dark energy weakens all the way to 0 and then flips negative, gravity wins. Expansion reverses. Galaxies fall back together. The cosmic microwave background gets hotter. Temperatures rise everywhere. Everything collapses into a singularity. Like the Big Bang in reverse. Some physicists think the crunch could trigger a new Big Bang. Paul Steinhardt and Neil Turok proposed this in 2002 as the cyclic model. Steinhardt told Quantum magazine in 2024, if dark energy continues to fade, it may indeed go all the way to 0 and then turn negative. DESI does not show dark energy reaching 0 yet, but it shows it heading in that direction. The third ending is the Big Rip. If dark energy gets stronger over time instead of weaker, expansion accelerates without limit. Robert Caldwell and colleagues worked this out in 2003. Galaxy clusters tear apart about 1 billion years before the end. Solar systems, 3 months before. Planets, 30 minutes before. Atoms, a fraction of a second before. But DESI actually rules this out for now. DESI shows dark energy getting weaker, not stronger. The Big Rip needs the opposite. So which ending does DESI favor? The honest answer is we do not know yet, but it points away from the Big Rip. It opens the door to either a modified heat death, or possibly, if fading continues, a big crunch far in the future. But dark energy is not the only crack in our understanding. There are 2 more. The first is the Hubble tension. 2 ways to measure how fast the universe is expanding give 2 different answers. The Planck satellite measured the cosmic microwave background and got 67.4 kilometers per second per megaparsec. Adam Rees and the SHOES team measured nearby stars and supernovae and got 73.04. Those numbers should match. They do not. The disagreement is 5 sigma, a 1 in 3.5 million chance of being a fluke. Even JWST has not fixed it. Wendy Friedman used JWST with different methods and got about 70, a third number that solves nothing. The second crack is the S8 tension. S8 measures how clumpy the universe is. Planck predicted fairly strong clumping, but when scientists looked at the actual universe using gravitational lensing, they found it smoother than expected. The Dark Energy Survey got 0.776. The Kids Survey found similar results. The universe is less lumpy than our best model says it should be. 3 cracks: dark energy changing, expansion rate disagreement, clumpiness mismatch, all in the same model at the same time. In 2024, a team at MIT showed that a single idea, early dark energy, could help with all 3 problems at once. It raises the predicted expansion rate, it reduces predicted clumpiness, and it helps explain why JWST found impossibly massive early galaxies. Naidu said, "We find that early dark energy is a very elegant and sparse solution to 2 of the most pressing problems in cosmology." Not everyone agrees. Colin Hill at Columbia has argued early dark energy makes some CMB fits worse. The fix is promising but not perfect. There is a historical pattern here. In 1859, Urbain Le Verrier found Mercury's orbit drifting more than Newton predicted. That tiny crack sat unexplained for 56 years. Then Einstein published General Relativity in 1915 and explained it perfectly. The crack was not an error. It was a signpost to a new theory. In 1887, Michelson and Morley tried to detect the luminiferous ether and found nothing. Another crack. That led to special relativity. Today we have 3 cracks. Colin Hill said if DESI holds, the textbooks that I use in my class would need to be rewritten. Adam Rees put it more personally. Sometimes I feel like I am providing clues and killing time while we wait for the next Einstein to come along. So how do we find out? We build more machines. We collect more data. DESI is not done. Its full 5-year data release is expected in 2027. If the signal is real, it should cross 5 sigma. Euclid, launched by ESA in 2023, is mapping 1.5 billion galaxy shapes. Major results start arriving in 2026. In August 2026, NASA launches the Nancy Grace Roman Space Telescope. Its field of view is 100 times larger than JWST. The Vera C. Rubin Observatory in Chile saw first light in June 2025. It carries the largest digital camera ever built. SPHEREX is mapping the full sky. The Simons Observatory achieved first light. China plans to launch Suntian in 2027. By about 2030, we will have data from all of them together. Joshua Freeman said our data is about to make bigger leaps. Willem Elbers said it plainly. As our data are getting more precise, we are realizing we may need something new to explain the results. We live in a universe made mostly of something we cannot see and do not understand. We just discovered that this invisible something might be changing. The force that decides whether the universe fades, collapses, or tears itself apart appears to be getting weaker. And no one knows why. 3 cracks are forming in our best model of reality. Together, they look like something deeper, something that might require an entirely new idea. Richard Feynman once said, "I can live with doubt and uncertainty and not knowing. I think it is much more interesting to live not knowing than to have answers that might be wrong. We are living in that moment right now. The moment where the old answers are cracking and the new ones have not arrived yet. And if you want to understand the other crack, the Hubble tension, the battle between two numbers that refuse to agree, we made an entire video about it. It is right here. I will see you there.